Alright, so we've got a uniform bar of length L and mass M that's free to pivot around its end by a very low friction pivot. Initially, the bar is suspended horizontally when it's released from rest. The rotational inertia of a bar rotating about its end is 1/3 ml squared. Determine the angular speed of the bar as it passes through its lowest point. So a few key ideas here. This is the initial position, and this is the final position in this problem. We're looking at this bar swinging through. And we're trying to find the angular speed. It's just framing what the problem is asking for. How fast is this thing rotating at the lowest point when it swings and the bar is vertical? If you want a visual for this problem, take your pen or pencil, hold the eraser, and then let it swing through. And the question is, how fast is it moving as it gets to the lowest point? Now, some students debate as to how to solve this problem, and I often see students saying, wait, are there two different ways to approach this? Some students say we can use the idea of torque, and we can say the force of gravity is pulling on this bar and applying a torque due to this distance away. And students say, look, the angular acceleration is equal to the sum of the unbalanced torques on a system divided by its rotational inertia. And then they say, we can use some angular kinematic formulas to solve this. Because you know that it's released from rest, and you know that delta theta is pi over 2, because it goes through a quarter revolution. The problem with this, though, is this angular acceleration right here is not constant. Because this torque is not constant. If we look at the bar at a later point, the force of gravity is pulling this way. But we have changed our angle. Now if I measure between the radius and the force, what before was a 90-degree angle now appears to be greater than 90 degrees. And that's going to change our torque. Because of course torque is R times F times sine theta. So not only do we want to know how to solve this problem, we want to be aware of how not to solve this problem and why this position or that approach won't work. The way we can talk about this problem is with energy ideas. What I'm going to pay attention to is a system of the Earth and the bar. That way I can say that this system is closed and there are no outside works, because there are no outside forces acting on this bar that are doing any work. The pivot is not going to do any work here. And I can take that out of here. And in the beginning, we have all this gravitational potential energy due to all that height. And then we're going to have kinetic energy at the end, and it is rotational kinetic energy. It's worth describing that that is rotational kinetic energy and not translational. Translational, if you take your pen again, would look like if the pivot was actually moving back and forth, if we saw it moving this way. Rotational is just if the pen is rotating about a stationary pivot. If it was translational and rotational, we would see it rotating and moving. So you look at that pivot to determine if there's any translational kinetic energy. And at this point, the pivot is actually staying still. The meter stick itself is just rotating. So now we know that we're talking about rotational kinetic energy, which will be 1/2 I omega final squared. Now a question of gravitational potential energy. Well, it's just the same gravitational potential energy we've always talked about, mgy. We need to determine a place where y equals 0, just like we do for any energy problem where we're using the conservation of energy. We need to define a reference point. And right here, we're going to define it as this point. That might seem weird a bit, but pause the video and think about it if you want to see, think about why it is that. And if you're back watching, or you just want to enjoy the show or you haven't figured out, heights are always measured from the center of masses. So we have to look at the center of mass of this bar at its lowest point, and then the center of mass at its highest point. And that's the change we care about. Other parts of the bar go through much smaller changes in heights, and other parts go through much bigger changes in heights. We don't care about those. We look at the center of mass. Whereas if we had to concentrate the mass on this uniform bar, it would be right at the middle. That's the height we care about. So it means that our initial height is L over 2. That's how high above the center of mass is in the beginning, because the whole bar is a length L. And then I'll plug in my value for I, which I'm told in the problem is 1/3 ml squared times omega final squared, and there we go. We can express our answer in terms of the given variables, which are m and L and any fundamental constant. And let me rewrite that over here for clarity. And we have turned a complex physics problem into an algebra problem. Okay. This over 2 is going to cancel with this 1/2. The m here is going to cancel with the m here. I wrote them as little m and big M, but it's all the mass of the bar. So what that is G times L equals, that's just 1/3 and then an L squared, so L squared over 3 omega final squared, or 3GL over L squared, or 3G over L equals omega final squared, or let me just do that right here, the square root of 3GL. Looking at that, I can see that that makes sense, because the units for that value would be meters per second squared divided by meters. The meters would cancel out, and then the square root of that, which gives me 1/seconds, which is what I'd expect for an angular speed, because radians is just a placeholder and doesn't actually have a unit. But that would be measured in per seconds, which checks out. And that is how we figure out the angular speed for this bar as it passes through its lowest point.